Hello, good afternoon everyone. We are the group 5. So let's move on to the activity number 10. Measuring the nightly path of moon. We have our learning objectives. First, students will be able to measure and plot on the graph the altitude and azimuth of the moon. Second, students will be able to analyze the moon's path over time.
We have the definition of terms. 1. Azimuth, the angular distance from the north or south point of the horizon to the foot of the vertical circle through a heavenly body. The azimuth of a horizontal direction is its deviation from the north or south. Second one, altitude, the angular elevation of a celestial object above the horizon.
So next definition of terms, we have diurnal motion, apparent daily motion of the heavens from east to west in which celestial objects seem to rise and set. And lastly, the angular velocity. It is the angular displacement of a body per unit of time.
The sky is always changing. The idea that the things in the sky are constant and unchanging is a common misconception. By observing the sky over just a few hours, students will see that the objects in the sky move, changing position in a regular way. So the moon's nightly path across the sky is apparent motion. This movement is actually an illusion caused by the rotation of the earth. The apparent motion of the moon across the night sky is a compelling example of how our perspective on Earth affects how we perceive celestial objects. While it seems that the moon is moving across the sky, this is an illusion caused by the Earth's rotation on its axis. As the Earth spins, celestial bodies, including the moon, appear to move, although they remain relatively stationary.
The Earth's 24-hour rotation causes both the sun and moon to rise in the east and set in the west. But the moon is also orbiting the Earth, completing one orbit every 27.3 days. This gradual orbital movement, combined with the Earth's rotation, creates the illusion of rapid movement across the sky. The moon's true slower motion can only be observed over several days by tracking its position relative to the stars.
Moonrise and moonset are times when the upper limb of the moon appears above the horizon and disappears below it, respectively. The exact times depend on the lunar phase and declination as well as the observer's location. When you check moonrise time over several days or a period of time, you will notice that the moon rises later each day. That is because the moon is orbiting the Earth. The difference each day is fairly consistent, but has several variables like your latitude. The time of day that the moon rises or sets depend on its phase.
Unlike the sun, the rising of the moon changes from day to day and location to location because the moon is orbiting the Earth. The moon takes just over 27 days to complete an orbit around the Earth, so you can actually trace its movement in the sky from hour to hour. This is why a lunar eclipse only lasts for a few hours. That's how long it takes for the moon to pass through the Earth's shadow.
When we measure the moon's nightly motion, we are essentially measuring the rate at which the Earth is rotating. So this can be done by observing the moon's position in the sky at different times during the night. So the moon will appear to move westward at a rate that is determined by the Earth's rotation. While the moon appears to move across the sky due to Earth's rotation, it actually has its own independent motion. The moon orbits the Earth in a direction that is eastward, meaning it moves in the same direction as the Earth's rotation. However, this motion is much slower than the Earth's rotation, so we don't perceive it directly.
And this measurement made in a single day is really measuring the motion of the earth as it spins on its axis. Think about it. If the moon takes 28 days to circle the earth just once, it wouldn't move very much at all in just a few hours. The earth spins much faster than the moon orbits. Earth takes just 24 hours to spin once, rotating 15 degrees per hour. Now let's proceed to the concept check. Number 1. Why does the moon appear to move across the sky at night? It is because the earth is rotating on its axis. As the earth spins, we see the moon shift its position against the background stars. Next, what direction does the moon appear to move in the sky? The moon appears to move from east to west across the sky. Last, how can you track the moon's movement? We can track the moon's movement by marking its position in the sky at different times throughout the night. You can use a compass to determine its direction or the azimuth and note the time.
These are the materials on making an astrolabe. First is astrolabe template, printed on cardstock or copy paper, scissors or hole punch, tape, string, paper clip, and straw. These are the steps on making an astrolabe. First step, cut out the astrolabe template on the black lines. Step 2, cut a length of string about 25 centimeters or 10 inches long. Tie a paper clip to one end of the string. Step 3. Poke a hole in the corner of the astrolabe using scissors or a hole punch. Tie the other end of the string through the hole. Lastly, cut a straw about 13 centimeters or 5 inches long. Tape it to one edge of the astrolabe. See the template for exact placement. We have here two materials, an astrolabe and a compass for measuring direction or compass on the cell phone. The first thing that you need to do is you need to measure the altitude from the base of the moon to where you are. This is your baseline distance. Get as close to the ground as you can. Look through the straw with your eye near the 90-degree mark. Move the astrolabe away from your eye. Read the angle by looking at where the string crosses the angle markings. This is the waving angle. The next thing that you need to do is to measure the azimuth of the moon with a compass. The easiest way to do this is with a compass app on a smartphone. Point the smartphone at the moon and read the azimuth angle of the display. If you use a conventional compass, keep the needle aligned with north. Then look in the direction of the moon and find the azimuth bearing. Use the instructions that come with the compass to help you. Next is repeat the exercise, measuring the altitude and azimuth position 4 to 5 times. Measurements should be taken at least 45 minutes apart to ensure that the moon has moved measurably. Record your measurements, time, altitude, and azimuth neatly each time so you can graph them later. And lastly, the next day in class, plot out your moon position data on a graph as shown below. You can use color dot stickers to plot the moon's position and color in the face if you like.
Hi fellow stargazers, here's a quick video to show you how to measure the height, the altitude of the moon, and the azimuth, the degrees from north that the moon's located in. So you can use those measurements to make your moon calendars. So here's our astrolabe, and you simply look through here, point it up to the object that you want to know the altitude of, and for us it'll be the moon. So I'm going to pretend like my moon is right there. And I'm holding it up. And then I can see here it's 30 degrees. You read this number right there. So it's 30 degrees higher than the ground level, which is 0. Altitude's pretty straightforward. Azimuth is a little more involved. For azimuth, you want to know how many degrees from north your object is along the ground. So use your imagination and pretend like you're sitting in the middle of a giant circle. A circle has 360 degrees. We're going to practice that really quickly. So for me, my compass is facing north right here. So I'm looking at my compass. North is this way. That's 0 degrees of the circle. Now if I made a quarter turn to the right that's facing you, that's 90 degrees, or east. Now if I make another quarter turn to the right and face south, that's 180 degrees. I'm going to make one more quarter turn and face west. That's 270 degrees. And one last quarter turn to go back to north completes a circle, which is 360 degrees, and it's also 0 degrees where we started. That's the degrees that you want to measure. That is the azimuth that you want to measure to find the moon and to record that on your calendars. So I'm going to demonstrate that, how I would find that right now. So I'm going to pretend like the moon now is here, facing that direction. So how do I use my compass to find azimuth? I'm holding my compass right now, and when you hold your compass, hold it flat, but I want to have my compass facing north still. It's pointing north still, and I'm facing the moon. So I'm pretending like the moon is right here and my body's facing the moon, but I'm holding my compass just in front of me, but it's still pointing north. Now you want to line up the dial on your compass to where north is right lined up with north, and that's 0. And if you do that, then what direction you're facing, you just read your little dial on your compass. And mine says east, and right here I counted with you yesterday in the video on our class, and I counted each little mark is 10 degrees, and here I'm counting 90. So I'm facing 90 degrees, which is east, and that's where the moon is for me right now. And that's how you can use your compass to find azimuth. There's another way to do it too, using your fists. If you know where north is, which for me showing this to you, north is right here. You know where north is, you can use your fists, which are 10 degrees each, to measure the azimuth of where the moon is, the distance the moon is from north. So I'm going to hold out my fist towards north, which is 0. And I said each fist is 10 degrees, and I'm going to go 10, 20, 30, 40, 50, 60, 70, 80, 90. And there it goes right under the moon, and that is 90 degrees azimuth. So you can use your fists too to measure degrees. I hope that was helpful. Now go outside and find the moon, and I'm looking forward to seeing what you record, the measurements you record. And don't forget to record the time, and also draw the moon. And when you draw the moon, you can just use a pencil, and you can draw the circle and fill in the shadow part of the moon, and you can also fill in the light part of the moon. You can use colors if you would like, or you can just make it black and white. It's up to you. But I'll see you next week. Look forward to seeing you guys.
Now, on this slide, you see how we graph the moon's altitude and azimuth. When we see anything moving, one natural question to ask is, how fast is it going? There are many ways to answer such a question. It is common to measure speed in either miles or kilometers per hour. This is not only the way to measure the speed. When something moves in a circular motion, like the moon circling the earth, we don't measure its change in distance because the moon is always about the same distance away from the earth. Instead, we measure degrees instead of miles or kilometers. So when students record the compass direction of the moon in degrees, they are measuring the moon's position by adding the time of the day to each observation, and they will have everything they need to measure the moon's angular velocity and degrees per minute. As you can see in the table, to get the degrees move, we are going to start with the position number 2, which is the 202 degrees, and we are going to subtract it with the value above, which is the 185 degrees, resulting to 17 degrees. And you are going to do the same process in number 3 and number 4, which results to 12 degrees and 19 degrees. And getting the time change, we are going to use the same method that we used on getting the degrees move. Compute how many minutes are between 7:18 and 6:15, which results to 63 minutes. And you are going to use the same method on number 3 and number 4, which results to 48 minutes and 68 minutes. So to get the velocity, we are going to divide the degrees move to the time change, which is 17 divided by 63 is equals to 0.27 degrees per minute. 12 divided by 48 is equals to 0.25 degrees per minute, and 19 divided by 68 is equals to 0.28 degrees per minute. So how are we going to use, or how are we going to get the average velocity? To get the average velocity, we are going to add all the degrees move, which is 17 plus 12 plus 19 is equals to 48. Also, we are going to add the time change, which is 63 plus 48 plus 68 is equals to 179, and we are going to divide those results. So 48 divided by 179 is equals to 0.268 degrees per minute.
So, to wrap it up, here's a quick recap of what we've learned. First is the moon's apparent motion is primarily due to Earth's rotation. While the moon orbits the Earth, we see it move westwards because of our spinning planet. Second is simple tools like compasses and astrolabe can help us track the moon's position by recording the moon's direction and angle above the horizon at different times. We can map its path. And lastly, analyzing the moon's path reveals patterns related to Earth's rotation and the moon's orbit. This data can help us understand the relationship between these celestial bodies.
That's all, and thank you.